Hello everyone, good morning. So we are all set to start the lecture today, and yeah, so we have discussed um, 5 different insurance products in this chapter, and we discuss about how we can calculate the net premium or the net single premium, which is the present value of the future benefit in different ways. And we discuss about how uh, we can compare and contrast in between these different insurance products with respect to the continuous life and discrete life, future lifetime random variables. And if I recall you quickly, so we had whole life, term life, pure endowment, and then the endowment, which is a combination of term life and pure endowment. And then we had a deferred whole life insurance, and all of them were first discussed under the assumption that the premium or the we didn't consider about the premium. Actually, the benefit is paid at the end of the uh, year of death, and the amount of the benefit is equal to one. It can be 1 rupee or $1. We once we calculate this net single premium or the present value of the future benefit, we can multiply it by the actual benefit. So it will give the present value of that actual benefit. And when it comes to the increasing or decreasing cases, we discussed how we can define or define an insurance product based on these two different concepts where we have level benefits during the uh, year and increase it by one uh, amount of like 1 unit of money or the currency we consider. And the other one was continuously increasing case where uh, the amount of benefit is proportional to the time, and it's uh, discrete version or for the discrete version also we have this one, and also for both cases we have a decreasing uh, term as well, but for the decreasing uh, benefit, so we have to like define it for a term because we have to start it from somewhere and then decrease uh, the same amount or different amount at a time, depending on the timeline. But up to this point, our timeline was divided into 1 year time intervals, and we had some uh, different equations to calculate these present values at the level premiums and also the variance of these present value random variables. And then we had a quick glance at the non-level benefit insurance, where the benefit is also differ uh, according to the time. And we saw how to calculate these present values using life table, and also if we were given the survival function, we can also find that because it's finding the survival probability is the most crucial thing, and then we can multiply by the corresponding benefit payment at that time to get the present value with respect and also multiplying with respect to the correct discount factor from there. So that was the total uh, picture that we have created regarding these benefit payments in 5 different insurance products. Now we are going to discuss about the employee life insurance part, where the benefits are being paid at different intervals. For an example, someone can buy a life insurance where the death benefit is paid at the end of the month of death, or the death benefit can be paid at the end of the quarter of death. And also it can be uh, an interval of weeks as well. So if we approximately we have 52 weeks, and then M become 52. If it is quarters, M is 4. If it is monthly, M is 12. Like that, we can uh, have kind of a discrete version which is compounded in different time intervals. And also suppose if we consider the uh, biannual interval, then 2 years would be equal to one uh, payment period. That means M should be half, because um, that we have only spent half of the interval when we complete the first year. So so this M is kind of a measure uh, on how we divide the timeline of the future lifetime into equal intervals. So future lifetime starts from 0 at age X, and suppose it's, so we usually divide it to 1 year intervals first, and this M is referring to how we could divide this 1 year interval into equal parts, but with respect to 1 year. So that means if this is M is 4, then we divide the year, or we consider 4 equal parts of an year. So that means by summing up two or the 4 quarters, we will have one policy year. But if we consider it as biannual payment circles, so then we consider 1 year as a half of the benefit year. So the benefit is paying, if the death occurs in here, the benefit is being paid at that point. If the death occurs here, still the benefit comes under here. So that means 1 year of a calendar is a half of the policy year, or the benefit circle. So then our M should be half. So that's the uh, definition in this M. So we can uh, have this current random variable using this function, which discretize the continuous future lifetime random variable into M equal intervals with the same equal width. So for an example, suppose our Tx, if Tx is let's say 21.6, so then suppose M is 4, then we divide the year into 4 equal parts, and the corresponding value of this one is given like 4 times 21.6. So let's multiply 21.6 by 4, and it gives you uh, the value inside this bracket is 86.4. That means the bracket indicates that we should extract the integer value within the number. So the integer value with 86 now, and divided by 4 gives us 21.5. That means 21 and 2 halves. So it says this person has, so now the interest rate or the benefit payment period is 3 months, which is a quarter per year. And this says this person has survived complete 21 years and 2 quarters. So that's how we interpret it. That means if this was like 12, m is equal to 12, then it says how many complete years and how many partial intervals that they have survived. So we can calculate this for an example. For the same case, if we multiply 21.6 by 12, the value is 259.2. That means the integer part is 259. When we divide by 12, it says 21 years and point 586. That means uh, if we convert 0.586 as a int or the fraction, so it's 7/12. So same concept. So I will write down it as if m is 12, that means we are paying the benefit at the end of each month of the death. So if the death occurs in the first week of January, the benefit is paying at the last day of the January. Likewise. So for the same tx, we can have kx as 12 and 12 times 21.6, and this will gives you times 259, because the integer part is 259. This is equal to 21 complete years and 7 months. So this is a mixed number. We have an integer, we have a fraction. So now you can see how clearly the behavior of this kxm random variable. So this special random variable means that we divide the year into m equal fractions. So year is a calendar year in here, but because in this case, the policy year or the benefit paid for the policy year and also the calendar year is equal. But in the case of like the policy years being 2 years of calendar year, so then m become a fraction. Uh, so in the first example, we divided the 1 year into 4 equal parts. That means 4 quarters, which includes 3 months per year. But in the second case, we divided uh, a calendar year, uh, which is equal to the policy year, to 12 equal parts. In that case, so this has to be 12. Uh, in that case, we have equal 12 intervals per the year. So depending on the value of m, so we will have kind of a mixed number, which is the complete number of years of survival and the total number of fractional times that they have survived. So let's visualize this in here. It says, so 21 in here and 22 is here. So if we divide this into 4 equal cases or the intervals, then the actual value is 21.6, which is somewhere in here. And that is the tx value. But the kx says, the kx4 gives this person have survived up to this point, and then the death occurred within this interval. So then the benefit is paid at this point. So this is the starting of that interval, and we almost sure that the person has survived up to this point, and then the death occurs within this interval because the actual death is in here. So that's the visualization of this random variable. Then um, we can calculate the probability function of this kxm plus 1 over m. Because now we know that even from this visualization, we saw the person has to survive up to this point and then get this 1 over m period. That means uh, we need to find the survival probability up to this point and then the death probability from here to here. That means the usual um, deferred death probability question. So we know how to calculate the deferred death probability when we are given uh, a time. So in the discrete, which means the annual discrete case, the kx started from 0 and then started to grow one by one. 0, 1, 2, 3, 4. But in this case, uh, it grows like from 0, 1 over m, which means one part of quarter, two parts of quarters, three parts of quarters, like this. It grows uh, in a way uh, where it shows the number of quarters that the person has survived. So that is how we can distinguish in between the full or annual K and the empty K. That means the probability of this Km x being equal to simple K is that, so if this is K, that means the death occurs in here. So the K in here. So we are almost sure the person is alive at this point and dead by this point. That so in general it is Tx in between K and, so if this is K, the next timeline we get is K plus 1 over M, which means if this is the half of the year, so the third quarter starts uh, from this point and end from this point before the start of the fourth quarter. So we just need to add 1 over M. So if you could remember in the annual case, we knew the person was alive at K and death has occurred in between K and K plus 1 because M was equal to 1 at that time. But in here, now the M is 4. That means uh, in our usual example, it has to be like in between 21.5 and 21.75. So, but we prefer to use the half because it's easy to calculate this interval. So if you were like be familiarized with these calculations now, I always define in terms, so the present value calculations as jumps. So then it's easy to calculate how uh, far we have to go back or go forward in terms of the time interval that we are considering for the interest rate. And in here, that's why we always prefer to uh, define K in terms of 1 over M's. So we know that if this is M is 4, we know that how many quarters that they have survived. If this was M was 12, then we know that how many months they have survived. So then it's easy to work with and it's easy to digest and find the number of months they have survived, number of quarters they have survived, number of years they have survived. So that's why we always prefer to have the full integer and the fraction like a mixed number there. Then we can find the present value and the variable. We know the present value is, so start from here and death occurs in between K and K plus 1 M. So in here, let's say the death is in here and Km value in here. If I add 1 over M to this Kmx, so then this is the interval that death occurs. So the benefit is being paid is at that point. So we will jump backward like this up to this point to calculate how far we should come back using the compound interest rate. So this should be like kx plus 1 over m, and I'll write it down like this: v k x m plus 1 over m. So that is the power, and we know that v is 1 over 1 plus I. So I is, now we have to use, so for the v, it's I m. Now we have to use, because I is the interest rate considered for the entire year. So IM is the interest rate considered for the mth time period. So the actual present value should be, as always, v to the power k plus 1 over m. And in here, the k is given as the years. So that's why uh, we get it, if we decode it like this, let's say we can expand it. So if k is equal to 0, so then the death occurs between the first time interval, so that the payment is being paid at this point. So then we have to take it back once. And the probability of death occurs in between this period is the person is alive at X, and the death occurs in between this 1 over M period. And if death occurs in the next period, that means we have to jump 2 times back. So our K is equal to 1, and we will come back this much of term. So that means 2 1 over m's. That's why we use k plus m in here. So now the death probability is person was alive in here and alive for one more 1 over m interval, and death occurs in the next interval. And let's have one more. So when k is equal to 2, that means death occurs in between these two, and we have to pay the benefit at this point, and that means to get the present value, we have to jump back 3 times. That is k plus 1 over m. So we will jump 3 uh, intervals back. So v to the power 3 over m is the discount factor, and the probability of death occurs in between this interval means the person is live during the first 2 intervals, and death occurs within the next interval. So that goes to the infinity. So this is the expansion, and the logic is clear now. So we can simplify it using this summation. So this is the actual present value of the net single premium of a discrete whole life insurance where the benefit is being paid monthly. So if M was 4, it's quarterly benefit paid whole life insurance. If it was 12, then it's monthly benefit paid whole life insurance. So that is the big picture of them. And in the same way, we can define the actual present value or the net single premium of a unit benefit monthly n-year term life. Now, we know that the lifetime or the lifeline is in between 0 and n. And after that, we don't have to pay anything. So we have divided this into equal m times n cap. So this is 1 over m, and if this is 1 year, Uh, no, let's say like this. Yeah. So in the quarter case, so we have years like this, the first year, second year, up to nth year, and each year is being divided into 1 over m cases. That means altogether we have n times m equal groups from 0 to n. So these are the total intervals in this covered or the insured period. And the final interval, which is the nth interval, m times nth interval, is this one. That means if the death occurs in between these two, so the benefit is being paid at this point. So the person has to survive up to m times n minus 1 intervals. So that's why k starts from 0 and goes to m times n minus 1. The summation comes up like that. And if I expand this, so in this first interval from 0 to 1 over m, that means we have to take only one m back, and the probability is death occurs between the next 1 over m case. And for the second interval, we have two jumps to come back, and the death probability is surviving for 1 over m times, and death occurs within the next 1 over m times. And for the next three cases, death occurs between 2 over m and 3 over m, and benefit is paid at the end of the 3 over m. That means we have to survive two 1 over m periods, and death occurs within the next 1 over m. And this continues. And the last term is this person. So we have to, so the benefit is being paid at this point. So that means we have to take jumps back to 0, and all the jumps are equal to n times m. And then the death is being like this. So this person has survived m times n minus 1 intervals, and death occurs within the final 1 over m interval. So this is the summary of this summation. It's a finite sum. And so now you are uh, in the way to define the employee endowment in-year insurance, because as we mentioned in the previous case, the PO endowment is only paid at one point. So no matter what, the benefit is confounded in different time intervals. The PO endowment is being paid at the end of the coverage period. So that means if we have an endowment insurance with employee benefit payment circles, so this employee interest rate only affect the term life part. The PO endowment can be taken as an annual jump back if we have the annual interest rate. But if we have only the employee or the IM, so then we have to jump back n times m jumps to 0. So depending on that, you have to get it back. But we know an equation to get or convert in between IM and I. So if you know IM, you can get I and then calculate this back to here. So it says if the death occurs in between 0 and n, this is how the benefit is compounded and calculated the present value. But if this person survives up to the n, then the survival benefit is paid as a PO endowment at the end of nth year. So it can be uh, compounded using this annual interest rate. So for that case, we have the uh, survival probability from 0 to n. So that's the uh, three equations that we can discuss under this empty compounded insurance. And now we can jump into this example for a 2-year insurance policy so that we can easily uh, see how we can apply this concept into a such case. So they says the coverage is for 2-year time. The contract only valid for 2 years, and the death benefits are payable at the end of half year of death. That means if the death occurs in between January or 1st of January and the 30th of June, the benefit is being paid at the 30th of June. And for the rest of the deaths, the benefit is paid at the 31st of December. And the amount of death benefit is paid 300,000 for the first half of the year and then increase by 30,000 per half of the year. That means we have only 2 years, 0, 1, and 2, and we have divided into equal 4 uh, intervals. Or an year is being um, divided into 2 cases. So the total length is divided into 4 equal parts. The benefit is starting from 300K, and at each step we add 30K more. So these are the benefit payments that we can expect during this coverage period. And they have given the death probability from x to 1 and x plus 1 to x 2. So the compounded or the halfly compounded interest rate is 0.18. And the death are assumed to follow a constant force of mortality between integer ages. So we need to have at least one of these two assumptions, which is the constant force assumption or the uniform distribution of death assumption, to do the calculation. So because we are calculating the death probabilities for fractional years, so here we need to stick into the constant force of mortality assumption. And the Z is the percentile random variable for this insurance. We need to find the probability that Z is greater than this. So to find this one, since we have only 4 cases for Z, so we just need to find uh, the Z or the corresponding value of Z and the probability of that event. So let's start by um, summarizing the information we have. Since the half year payments are done, so M is 2. And then we can have the curtailed half year random variable like this. So this can be 0 at this point, 1 at this point, since it is 2 intervals, so 1 over 2 is this half, and this is 2 over 2, which is 1, and this is 3 over 2, because we have 3 halves, and this is 4 over 2. So that is the easiest way to get these possible values for this kx. So if death occurs in here, then k goes from 0 and the rest of the path is here. If death occurs in here, the k is here and 1 over m is in here. And if the death occurs in here, the benefit is paid in here and the person was alive at this point. So it's easy to visualize the scenario now. So those are the possible values for the curtailed future lifetime random variable. And for all the other cases after the second year, the C is equal to 0 because there's no benefit payment at that time. So we only have to calculate the present values of these cases and the corresponding probabilities of them. Then we can find which values gives us a value greater than the 277,000, and then get the corresponding probability from that. So let's start by calculating the first probability. Which is the probability that kx2 is equal to 0. That means the death occurs in between these two timelines or the time uh, margins. So the person who is at age X, the death occurs within the next zero point 0.5 years. So since the constant force of mortality is there, we need to convert this into the survival probability and apply the constant force of mortality assumption. So we convert it into the survival and then apply the constant force of mortality assumption. So this is how we get it. And we are given Qx1. So it is 16. So Px1 is 1 over 16, which is, so this is not 1 minus 0.616. So this is 0.84. So yeah, sorry, this is a constant force of mortality. That means we need to get it as a power like this to the power. And Px is 1 minus 0.16. Then the answer is 0.84 square root of this one. So then we can get that probability as 0.0834. And so that is the probability of being k being equal to 0. And the present value of this case at this time is the payment is 300,000. So we have to get it back by one jump. That means 300,000 multiplied by 1 discount factor. So the I2 is 0.18. That is the compound interest rate for the annual rate. And if you could remember, so we mentioned that I2 over 2 by 2 equal to 1 over I. So that means this says if the interest rate being calculated for half an year and the corresponding annual year rate means on I2 divided by 2 and 2 halves. So that means we need to divide this I2 by 2, which is 0.09. And since we have only one jump, we don't have to consider the power because it's 1 and it's same. So the value gives us 275,000 and 229.4. So that is the corresponding present value of that case. Then we can quickly calculate the other probabilities using the same concept. Now this is equal to 1. That means the probability that X survives for half an year and death within the next half an year. So that means survives for half an year and death occurs between the next half an year for a person who has already survived half an year. So yeah, this is the probability, and this probability is same as the difference in between the death probabilities at the end of 1 year and at the end of 0.5 years. So this one is given 0.16, and for this one we calculated it in here is 0.0834, which is given like 0.765, and the corresponding z value is, now the death benefit is 330,000, and we have to get it back by 2 jumps. So the discount for 1 jump is this. For two jumps, it should be this. And the corresponding value is 277,754.4. So that is the present value. And the next possible value is this. So this is actually, this is 1 over 2, and this is 2 over 2 because we have it's in half. This gives us the probability that the person has survived 1 year. That means 2 half years, and death occurs within the next half year. So we know that this person has survived 1 year and death occurs within the next half year. So for this one, it is given, and we can take it by 1 minus 0.16. And for this one, again, as in the first case, so it is 1 minus 0.23 means 0.77, and the square root of that one. So it gives us 1.29 as the probability, and the corresponding z is 360,000, and discount has to be 3 jumps back, 1, 2, and 3. So the corresponding discount factor and 3 to the power. So for that case, it's 277,986.1. And the final value Kx is 2, that means this person can survive up to this point and death occurs in the next interval, then there will be a benefit payment at this point. So we will take this probability as probability of surviving for 3 half years and death occurs within the next half year. So this corresponding probability is the difference between the death probability at 1.5. So 1.5 is here, and the death probability now this has to be in the other way. The second year, at the end of second year in here. So death probability is greater than, so this death probability is less than the death probability in here. So the difference is on the other way, and we can take this as, so we know this probability, it's we can write it down. For this one, it's point surviving the first year, and yeah, I think we can take it on the other way. See. Because we know that the difference can also taken using the survival probabilities. Okay, now it's easy to calculate because we have the constant force of mortality. So that means surviving in the first year and the surviving in the next half year, and surviving in the first year and the surviving during the next year. So probability 0.9029, and the value of Z is, and we have to take 4 jumps back. So the discount factor is 1 over 1.94 to the power 4, and the benefit is 390,000. So the present value of such benefit is 276, 285.8 with this probability. And for all the other cases, the survival value is 0. So that means also when probability that kx2 is greater than or equal to 2, we can sum up these 4 and subtract from 1. Then it gives like this, and corresponding Z value for this is 0. So then we don't have to worry about that. Now we can check these values. This is 277. So this is greater than, this is greater than, this is less than. So this is, so these are the two occasions where we can observe a present value which is greater than 277,000. That means if we sum up these two probabilities together, we can get this probability, which is equal to probability that kx2 is equal to 0.5 plus the probability kx2 is equal to 1. Summation of this one and this one. So that is the corresponding probability. So now you can see, so in the empty case, we have to carefully look into the timeline and build, depending on the need, So here we calculated the probability, but we had to like stick to the uh, partial or uh, the assumption which can be applied to find these probabilities in between integer years, and also um, the present value and the corresponding probability of having that present value. So the probability is taken by referring to the timeline. So we have to be more practical and think each case one by one and get the probability, and then get the corresponding present value. So if you know the probability and the present value, and you can find the expectation and the variance and this probability. So you can do three things once you build this uh, distribution. So I will, as an additional step, I will write down the distribution of the probability distribution of this. So it's 0.0834 when k is equal to 0, 0.0765 when k is equal to 0.5, 0.1029 when k is equal to 1, and 0.09029 when k is equal to 1.5, and 0.6468, which is 1 minus the summation of first four probabilities is greater than or equal to 2. And this is the probability distribution function, or the density distribution function of this future lifetime random variable. So these probabilities are also same for this, let's say, the distribution of z. So at the same point, you can find the z is equal to 275,229. C is equal to 277,54754, and C is equal to 277,986, and C, in this case, C is equal to 276,285, and C is equal to 0 for this case. So with this attempt, you can find the probability distribution of the future lifetime and also the probability distribution of the present value distribution. So if you are asked to calculate the probabilities of this or this, you can find the corresponding probability by referring to this distribution, because we calculated this value by our own. And if you want to get the expected value, you know the value and you can the corresponding probability. So these are the values for the future lifetime. These are the values for the present values. And these are the probabilities for corresponding case for future lifetime or the present value. So you can get the expectation or either the uh, expectation of the first as the first movement and the second movement, and then calculate the variance using this. So we in here the motive was using this information, we built the probability distribution of k and z. Both have the same probabilities. And the other thing you need to keep in your mind, so if the compound probability is given like I2, so then you have to divide it by the corresponding m. In here it is 2 before getting the uh, present value. And also you so that how to apply the constant force of mortality in between integer ages. And yeah, so in here we use the death probabilities, but in here we use the uh, survival probabilities. So now we can move on to the recursion topic. So Yeah, before going to recursion, I will summarize these parts in terms of empty. So if I go back to the topics of these different insurance products, so I mentioned uh, for the discrete case, the discrete endowment insurance, we have the term life plus the pure endowment, and for the continuous case, it's continuous for the term life, but the pure endowment is one-time payment. So there's only one payment in here. So these are the two types of equations for the term life. And if you apply the Empley equation, so we mentioned we can get this like this. And in the same way, we can get the whole life as a summation of term life plus the deferred whole life. This is same as, the concept is same as getting the continuous whole life, continuous term life plus continuous deferred whole life. That means if you want to get it empty compound derivation, so you get empty derivations of these uh, empty compound whole life, empty compound term life, and empty compound deferred whole life. So that is the story of these three relations between the term life and the endowment and pure endowment, the term life, whole life, and the deferred whole life. So you can have three different varieties. This is the annual case. This is the annual in continuous case. This is the empty case. And you have six different equations uh, under this. And now let's define this deferred case, because in that case it says after n years the insurance starts. So we can have first, let's say, take it for the annual case. So in the annual case, the deferred whole life says after n years, we have started a whole life from there. So that means you have to survive up to n years and then start this whole life. So since we are still at age x, so we need to take this back by v to the power n to get the present value. So same concept is applied for the continuous case. Still, we have to take it back from n years, and to get it back n years, first we need to survive up to n years. So the survival probability comes. If you survive there, so this is the quantity that you need to get back. So this is the present value by that time, x plus n time. And this is how it works. Then the empty case says, still you have to survive n years, but at n, now your age is x plus n, and the whole life is compounded m3. So now you can see this v to the power n pxn is same for all three cases. And if you could remember, for the PO endowment, we used this notation, which is equal to, for a $1 case, this, and also this. So all these three have the same meaning. So whenever you find the PO endowment, it can be interpreted as the probability of surviving up to n years and discounting it back n years. And the same notation, it says the expected value of $1 payment in n years in here. So these are the notations that you need to um, familiar with in this case. And the important thing is, though you are differing, so though you are calculating the compounding the benefits in monthly intervals, still you have to consider uh, the deferred period in years. So this PO endowment part or the future jumps are compounded annually up to that point, and after that we have to start the monthly compound in here. So this n is number of years and m is number of intervals you have divided uh, the year into equal parts. So those are the things we need to be familiar when you're dealing with these calculations. Then we can move to the recursion part where we use these equations to jump into one step ahead, or if we have a probability at this point, we can look back one step back using these recursion cases. So the whole life, let's visualize it like this. So at age X, you start a whole life. So at age X, the present value is AX. If you start it at X plus 1, the present value is at this point AX plus 1. So in between these 2 years, so the Tx is 0 at age X. And if you are, so since it is Tx, now the Tx goes from 0, 1, and so on. And then you have, so you can face two cases or two incidents. So in this interval, the person can survive, and or the person can uh, face the death. That means we have two options with two probabilities. So after AX, if the person dies in between this these two intervals, so then the benefit pay, so in this case it's $1 because the person has died. And if this person has survived, then starting from there, we have a present value of the whole life insurance. So these are the two cases. That's why we have to get the uh, present value of these two, which means the expectation of these two cases with using these two probabilities. So the present value of the whole life at age X is, if this person dies, the benefit is 1. So then 1 times V, because we have only one jump back. So V to the power 1 times plus times 1 times QX. If this person survives, so then we have another present value. So that means we have to take this A, X plus 1 back by 1 jump. So V to the power 1, P, X, and survive for 1 years, P, X1. And the amount we are taking back is AX plus 1. So that's how we define this. So you don't have to like memorize it without meaning. So now you know how to define it. So if you are unsure about the equation, you can check it by applying this concept. So this is same for uh, the term life as well. But in that case, for the term life, so starting from age X, the insurance is valid only for N years. So if you go 1 year ahead, the number of years that you have to survive has less, which means N minus 1. So this has to be minus 1. And it's like this. Let's say in here, from 0 to N. So the total period at age X is N. But when you go to age X plus 1, you have only N minus 1 remaining years. So that means with the same concept, if the person dies in between 0 and 1, the benefit is being paid. So the benefit is 1. That means 1 times V times death probability. And if that person survives, that person only has N minus 1 years. That means it is the present value can be calculated by considering a term life purchased at X plus 1, but the term is N minus 1 now. So that's how we define it in here. So we can write down, if dies, the benefit; if survives, there's another present value which is taken back by 1V. So that is the second recursion equation. And then for the endowment case, so we have this with the same concept. If you are at age X, you have N years ahead as the coverage time. But if when you are going to X plus 1, then you have only N minus 1 years as the coverage. So that means if this person dies between 0 and 1, the benefit is being paid. But if this person survives, we can consider that that person is purchasing another endowment, and that present value is AX plus 1 is the current age at this point, and he has to only survive N minus 1 more years. So now you can see, so we know that to find the endowment insurance present value, so we need to find the term life and the pure endowment part. But using the recursion formula, once you find the current value, or once you find, suppose at age X, you find the endowment present value. So then using that, you can find the future or the next year present value of this same insurance, with the same type of insurance. So on the other hand, if you are given the value of X, so using this equation, you can find what was the expected uh, like the present value of this endowment insurance if I bought this 1 year ago. So you can answer these two questions using this endowment recursive formula without calculating the pure endowment and the term life again. So those are the use of these things. And also you can create these equations. So which means you can derive these equations by yourself for other insurance as well. Just stick to this concept. We are only looking ahead 1 year, and within that 1 year, we have two possibilities: death or survival. If death occurs, the benefit pay comes, but the survival occurs, then we can have a suitable uh, insurance present value corresponding to the same case. In here, if it was whole life, then we had a whole life. If it was term life, we had a term life. If it was endowment, we had an endowment. And even for the pure endowment, you can apply the same concept and derive that by yourself. When it comes to the increasing and decreasing, so we will discuss on these two parts. So we apply the same concept. And for the second movement, as we discussed in previous case also, once you get the first movement, so you just need to replace deltas in the for the continuous case. We replace delta by 2 delta and n by 2n to find the uh, actual present value and the discount factor respectively. So for the discount factor, we know that log value of 1 plus I is delta. That means the V is equal to e to the power minus delta. So that means if you want the second movement, so your discount factor will be e to the power minus 2 delta. So that's how it works. And now for the empty case, it's a bit complicated in notation, but the concept is same. So if you have this interval 1 over m to 1 over m up to m times n, and it goes beyond and says, so now you have to survive only for 1 over m interval. So if death occurs in between this interval, benefit is being paid at this point. If survives occurs, so then now the age is x plus 1 over m. It's like if it was a quarter, so then x full years and 1 quarter year. So it's same as buying a full or whole life insurance at that age, and that present value considered all the future benefit payments compounded or the discounted back into this place, and this considered all the future present values or the benefit values and expectation of those present values corresponding to the benefits at this age. So you know this value, you can find this value without calculating it from scratch, uh, as we did in using the previous equations. So that is the story of this equation. And when we expand into the annually decreasing or annually increasing cases, it always occurs like that. And so these are only for your reference. So I will decode one equation for you. So we can get the idea of that one. Let's see this equation, the decreasing equation. So we say the decreasing equation of like the present value of an decreasing benefit annually for a term of n years. Then the equation says if the death occurs, the benefit is equal to n, and you have to get it back by 1 year back with 1 discount factor. If you survive, still you have to get it back by v, but once you survive, then we have a decreasing. Now the age is x plus 1, the remaining time is n minus 1, and a term is there. So this is the derivation is easy. But for the increasing case, if I visualize this one, it says like this. During the first year, we have the benefit equal to n, but during the next year, benefit is n minus 1. The next year, it's n minus 2, and this decreases up to 1 when you goes to n. So if I remove this first year, still the remaining is a decreasing step function. So that's why we could get this directly. But for the increasing case, let's say annually increasing present value of a term life, then if you survives, or let's say if the death occur, the benefit is 1, so we get it back. But if they survives, then that's a complicated uh, situation. So how to get that idea? Since like this. So during the first year, the benefit is 1. During the second year, benefit is 2. Then it's 3. And once it grows up, the benefit goes to n. That means if the death occurs, this benefit is being paid. If they survives, now their age is in here. So the remaining is also increasing. But if you get the area, so you have missed this area. So we need to consider this blue area as well, because for the increasing case, start from here and grow up on this blue block. So, but we have to consider this one as well. That means if they survives, there are two options. This part gives you the present value of a term life who's at age x plus 1. The term is n minus 1. And this part is, so this is an increasing case because it's like 1, 2, 3 up to n minus 1. And this is a level 1 because at each year it's 1. So the summation of these two becomes the next option for the survivor at that time. So for this one, the bracket, you get the summation. That's why we get the recursion of an increasing benefit paid annually for a term life at a of n years, who's at age x. We can recursively find the next year probability. But if that survives, there are two different products. One level term life and one increasing term life. So that's how we have these two terms for the increasing, but for the decreasing, as we visualized in here, it's according to the numbers, so we don't have any additional case, but in the increasing case, because of this, so if we get that increasing part, then we have to consider there's another level part as well. So that is the difference between increasing and decreasing cases in here. So then you can like simplify it more, and you will find that once you get this one and this one, you can like expand it. one step more, qx plus vpx I x plus 1 n minus 1 1 times vpx, the increasing benefit for the n minus 1 year term life. And this is also a familiar version because you could remember in here. So the summation of these two terms is the present value of the term life starting at age x. So now you can derive, like you can get this uh, present value of an increasing benefit for the n-year term in two equations. In this one or in this one, both gives the same final value, but it uses two different insurance. In here, level uh, term life at age x plus 1, increasing term life at age x plus 1, but in here, level term life at age x and increasing term life at age x plus 1. So using two different cases, we can have the same present value for the increasing case. So that's the story. And also, we can apply the same case for the life insurance or the whole life insurance. Now, you have to get rid of the term part. So it is the increasing whole life at age X is VQX. When the death occurs, there's only one payment. But when the survival occurs, then one increasing whole life at age X plus 1 and one level whole life at age X plus 1. So those are the equations in terms of uh, recursion for these uh, policies of whole life, term life, and endowment, and also for the monthly case. Now we can apply this concept into this example, and we can move on to the next section. So let's say for a whole life insurance of one on age 41 with death benefit payable at the end of the year of death. So it's annual payments. So we are given these probabilities. So we are asked to find the present value of the random variable for this, the variance of the present value of this random variable for this insurance. And it's like if the present value is calculated for this equation, it's age 41, the whole life, and it's discrete benefit payment. So this is the present value we need. And so this is the corresponding present value for this one. But to find the variance of this, C is the present value random variable for this equation. So if we had for the variance, we need this one and this one. So if you could find these two, so then we could easily calculate this variance. So in our the information they have provided, so they have given these values, but we have additional values as well. So if we could remove these two, then we can find the corresponding quantities and apply it for the variance equation. So let's start with this. So we know that A40, the present value of the whole life at age 40, is VQ40 plus VP40. If survives, it A41. And then we can apply it to here. So now we get A41 minus VQ40 plus VP40 times A41 is equal to 0.002. Now we can get A41 from this because we are given V. So we can find B using this. It's V, and we are given this P, so we can find Q as well. So this is equal to 0.00822 plus 1005 times 1 minus 0.9972 divided by 1 over 5 times 0.9972 plus 1. No, minus and plus. So this is the value of A41. So it gives 0.0. You can get it directly from the calculator like this. And now to find the second movement at age 41. So we can use the same recursive formula, but at 2 times mortality. So this is, so we replace V by V square, and probability is same. The probability is same, and the second movement of 41, which is needed. Then we can substitute it to here, and we directly get A41 is 0.0043 plus this term, because double the mortality, and probability is same, 1 minus 972, and this gives the value of the second movement. Therefore, we can find the variance as power this, which is this. So now you saw that if the information is given in 2 nearby integer years, and if that was given for both the first movement and the second movement, it's easy to stick to this and calculate. So for this, we should mention like this. So I mentioned that V is equal to, so in a separate note, V is equal to the minus delta. So for the second movement, we need to calculate at 2 times more force of mortality. That means delta become 2 delta, and this is eventually become e to the power 2. So that's how it's taken in here. So they replace delta by 2 delta and n with 2n. So here That's what we did. So that's how we can use these recursive formulas and play with these calculations. Um, it's not a new thing. It just says if you have some information about the present values of a life insurance for two adjacent integer years or uh, partial years in between integer ages, still we can find these values back and forth, or we can find variance and higher movements like a first movement and second movement using these equations if the informations are given for both in like the integer years. So you can do it. So apply that concept into many different insurance products. So in here, in the example, it used uh, the whole life, but we can apply the endowment or the term life or any other type of insurance. And now we are moving to the final part of this topic, uh, relating the continuous, discrete, and the employee insurance. So now it's time to like discuss the entire thing that we have discussed up to now in the under these continuous, discrete, and empty cases. So we saw that if in the discrete case, if we had uh, two nearby values, then uh, we can get the present value of one year using the other year's present value. So for the continuous case also, it's same and the empty case. And also we wrote down the similarities between the present value equations for whole life, term life, and the endowment in continuous, discrete, and empty cases. And what if like we could go back and forth in between these cases, like converting the discrete into empty directly or converting discrete into continuous directly. So we can do that under uh, the assumptions, two assumptions of uniform death distribution or the conserved force of mortality. So you know that under the UDD, we modified the death probability, and under the constant force of mortality, we modified the survival probability. And in here, we use this case uh, for the uniform distribution of death, and then we'll have the acceleration method, which is kind of a systematic way of um, linear, or it's kind of a linear interpolation of these values. So let's discuss about the UDD first, and then go to this one. So let's, yeah, we can use in here. So we knew that um, if we have this empty compound interest rate for M terms per year, same as the annual compound interest rate. So this gives you IM as 1 plus I or 1 over M minus 1 multiplied by 1. And now we can get this IM. So what you have to do is just multiply, let's say we have a correction factor and we multiply any kind of discrete present value with this correction factor to get the corresponding empty compound uh, present value for that case, like this. For the whole life, the person is at age X, and if we compound it emptily, then you can find this directly by multiplying this correction factor with the corresponding annual probability or the annual present value of a whole life at age X. And so that is the, let's say, UD, the uniform distribution of death. And the other type is acceleration of claims, which is the interpolation method. So we can say accelerated claims. In the accelerated claims, we multiply the correction factor, which is equal to, this is the annual interest rate increment, and we divide the year into m intervals. So that means we get 1 minus m minus 1 over 2m. So this is the correction factor. So that means for the same whole life, under the accelerated claim approach, we get, so this is an approximation, linear approximation, it's not equal. So it's approximately equal to m minus 1 over 2m and the corresponding whole life. And for the term life, level benefit in year term life, if you want m3 compound term life under UDD, the correction factor is I over IM multiplied by the annual term life. Under the accelerated claims, it's 2m and the corresponding term life. So we can extend this to annually increasing whole life. So increasing annually, it's whole life, and compounded monthly. Still, the correction factor is same, multiplied by the annual compounded present value. So likewise, you will get for this. And let's have annually increasing. No, let's say since we have increasing, let's have decreasing. Term life. So then it's decreasing, compound empty, and for in terms, correction factor is same, decreasing. For even for increasing, it's same. So you just need to change the notation there. So then under this approach, m minus 1 to m decreasing annually for this term. So that's how this. So these are all discrete cases. Under the same approach, if we want to get the continuous, if we need continuous case, my pen is not well. Now the adjustment factor will become I over delta. But in here, if m goes to infinity, so which means we are dividing 1 over 1 year to infinite small intervals. So when m goes to infinity, the factor goes like 2m, limiting m goes to infinity, gives you, if you divide these things and uh, substitute the limit, this is half. So that means these will be the correction factors, and I will do it only for the whole life. So the continuous whole life is given under UDD with multiplying by this factor with the annual discrete whole life. If you get it through the accelerated claims, then 1 over half discrete. And you can continue it for others as well. So we got this because when n goes to infinity, Im goes to delta, because you know that. So m is the number of intervals that we divide the year into equal parts or the equal intervals. So if we decrease the size of the limit, that means we increase this m into infinity. That means we are dividing the year into infinite number of small parts. So it becomes continuous. So that's the motive. So you can build these things accordingly. And I'll write down this for one more. Let's say if for increasing. So then continuously increasing whole life. The correction factor is this. And the discrete increasing case. And for this one, using this discrete, right? So that is how we can get this. And one thing you have to keep in your mind, when it's come to endowment, you cannot get this directly using this. That's the reason, because the discrete endowment is term life plus the PO endowment. So by multiplying this 1 year, or the one-time payment is not meaningful. So that means this is not equal to this. So this is, so if this should be equal to, the definition of this one is the continuous term life plus the one-time payment. So that means, therefore, this is equal I delta AX discrete plus one-time payment. So that's how it works. So this is under UDD. So if you want it under uniform acceleration, so you can replace this correction factor by 1 plus I over half to the power. So that is the value approximated using the accelerated claims. And you can apply it for increasing cases as well. So make sure that if you have only one payment, like the PO endowment payment, you cannot adjust it using these factors because it's one payment. But all the other series of payments that we are expecting, so we can multiply by these adjusting factors for UDD and the accelerated claims. So it will give the corresponding continuous or empty compound interest uh, and the present value of that one. So that is the story of these 4 points. And now we can quickly go to this example where we are given the I, the death probability at age X and X plus 1 for one more year. So we are asked to calculate the continuous insurance or continuously benefit paid term life insurance, term, actually this is a continuously benefit paid endowment of 2 years, assuming the UDD for fractional ages. That means at first we need to find this. So we can decode it like the summation of the present value of a continuous term life and the present value of the PO endowment. And for this part, under UDD, the correction is delta. I over delta, and delta is less 1 plus I. So the present value for this one, for the discrete case is there. And this. Now, we can find these two present values and delta separately. So let's say for this one, it's if death occurs in the first year, benefit is 1. If death occurs in the second year, the benefit is 1. So we have to get by 2 jumps. And you will get 1011I times Q05 plus 10101 to the power 2. And this is 0.95. And this is 0.08. So you get 124. So this is the present value of the discrete term life. And for this part, we get they have to survive for 2 years. So after 2 years, we have to discount it back. So surviving from X to X plus 1, X plus 1 to 2. That is, the discount factor is this, surviving this, and surviving this. So it gives 0.8567, and eventually, so we can find this in here, 0.0099. So the adjusted continuous present value is 0.0099 times 0.124 plus 0.8567, which is equal to 9814. So now you can see, so we can like as we have seen, we are comfortable with doing these discrete calculations because we can jump in regular intervals and define it by our own. That means if we assume the uniform depth distribution or for fractional ages, then we are able to convert that discrete value into the continuous case of the corresponding uh, life insurance product, or even under the accelerated claims. So that means we just need to practice the discrete calculations, then we can convert into continuous or monthly values accordingly. So that's the usefulness of those conversions. Then I will quickly remind you about the shortcuts that we have discussed. So for fractional ages, we use these constant force of mortality and the uniform distribution of death, or the Mobius law. And under the constant force of mortality, um, we knew that, like, this is the present value of a continuous continuously benefit paid whole life insurance, and it's directly taken through mu over mu plus uh, delta, because the force of mortality is a constant now. So that means, so initially we had this time varying constant force of mortality. Now it's this, and we mentioned, so we discussed this, like so when the distribution of future lifetime will become exponential or follow an exponential distribution when the constant force of mortality assumption holds. So you don't need to do any calculations. If the constant force of mortality and the interest rate is given, we can easily find this under the constant force of mortality, the continuously benefit paid or life insurance present value. So if you know this, you can convert it back to the discrete case using the previous conversion equation. And for this one, this is came through, like we know, it's v to the power n and p x n. So when v to the power n is e delta n, and pxn, since we know that pxn is the exponent of the integral of mu, since mu is a constant, so now it's exponent of minus mu, and it goes from 0 to n, so mu n. So that's how we got this value. And for the deferred case, again, we have these things. So if we could, like, buying a deferred whole life at age x means buying a whole life at age x plus n and discounting back n years. So this n has to go there like this. So from these two equations, it's like exn times a x plus n bar. So this is e mu delta n times. So in a x bar, we don't have any x terms. So that means it's also mu over mu plus delta. So that's how we got this. And for this one, it's term life. That means whole life at age x minus the deferred whole life at age x. So you can get this by this one and this one. So this is 1 minus 2. So that is pretty much straightforward. Once you figure out this one, so if you memorize this one and these two cases, you can easily get the other values derived. And under the yeah, so this is the constant force of mortality. And under the De Moivre's law, or the uniform distribution of death, we knew that the distribution of future lifetime is uniform, and it gives the force of mortality as this, because the density is 1 over this. If this is uniform, then the density of this uniform random variable is this. That is the force of mortality. And it will give you like this. And this is the annuity term, which should be discussed in the next chapter. So it's complicated, but this is not like applied directly, but we can. So in the annuity, we will find a way to calculate this using Z. So this is the present value of term or limited annuity, but we don't need to like stick to the annuity calculation directly, because we have a conversion from the benefit present value to the annuity present value. So we'll use that one, and we can easily find this using the same benefit present values that we have used to calculate. And for this one, it's Vn is usual discount factor, but the present the probability. So this is the survival probability. This says that the remaining part. So the whole probability is 1. That person has survived for n over omega minus x. So the remaining is 1 minus the survival, the death probability, gives the survival probability up to that point. So this is how we derived it. And those are the things we need to keep in our mind. So this is continuous. So we call it this annuity immediate. So we have 2 dots in here, but this is discrete. So we don't have any dot in here. We call it it's also annuity, but this is annuity due and annuity immediate. So we'll discuss those two in the next chapter. So those are the equations that we need to like get familiar, but we don't use this De Moivre's law frequently. But in the next chapter, we will discuss about these annuity calculations, annuity immediate and annuity due. So you will find how to do these calculations easily using the benefit payments. And that is the completion of this life insurance topic. So after a brief interval, we can start uh, this annuity